In this video, we're going to talk about approximating areas. So in our previous video, we saw that we can find areas if it's a triangle or a circle or something like that, but it's very rare that that's actually going to be the shape of an area that we're trying to find if we're talking about the shape under a graph. So to start off, we're not going to be able to find exact areas for other things, but we're going to try to approximate the area, get an estimate for what we think the area is going to be. So how can we approximate the area of this graph using simple shapes? So if you look at this kind of bluish area we're trying to find, it's not a nice shape. It's not a square, a triangle, or a circle. So we can't just use a geometry formula. What we're going to do is approximate the area using simple shapes. And the simplest shape in terms of finding an area is a rectangle. Because the area of a rectangle is just base times height. So we're going to use rectangles to approximate this area. And it's going to be an approximation because we're not going to get the exact area using rectangles. So for instance, we can start off with just one big rectangle. And that'll give us a kind of starting point for the approximation of the area we care about. It's not going to be perfect because there's this extra piece of this rectangle that's not actually part of that blue area I want, but it kind of gives me a starting off point. And then how can we get closer and closer to our answers? This is the idea of calculus in general, is we kind of get closer and closer to our answer until we get so close we know that's the actual answer. So then we're going to do this. Instead of using one big rectangle, we can use two rectangles. So maybe I can do something like this. One rectangle to the middle and one rectangle on the right. All right, this is going to be a better approximation because now if you look at the kind of area compared to what we want, we have some extra pieces here, and we're missing a bit there. All right, but in general, this big red part here we had before is not part of our new approximation, so this green area is going to be closer to the answer than the red area. And then we can make our guess even better by using 4 rectangles. Now there's some green parts that are not part of the blue parts. Now our blue estimate is even better. And the basic idea is we just keep doing more and more rectangles. You do 8 rectangles, 16 rectangles, 32 rectangles, more and more rectangles. Eventually the little bits, so if we had this really skinny rectangle here, the little bits that we have that are missing or extra are going to get so small that it gives us a really good estimate for the area. All right, so this is the basic idea of estimating areas that are more complicated. All right, so now I was doing our estimations. We had our rectangles, and the question is, how tall should I make this rectangle? I guess the height of the rectangle depends on, or gives us the area. So let's just say we had this shape here, and we were trying to find this area. All right, there's 3 different ways that I can make my rectangle. So the first one is called a left-hand sum. I'm going to use the left side of the rectangle to tell me the height. So if I'm making a rectangle, I'll go up to the left-hand part of my graph, and that's going to give me the height of my rectangle. All right, so that green rectangle would be the approximation if I'm doing a left-hand sum. If I'm doing a right-hand sum, I'm going to do the exact same thing, but I'm going to start on the right side of my rectangle, go up to the top where that hits my graph, go across and down. All right, so you see you get a different rectangle than the green approximation, which is a left-hand sum. So I'm going to use the right-hand side of every rectangle. And the last one is the midpoint. So instead of using left or right, I just use right in the middle. All right, that's going to give me the height of my rectangle. In this case, I get this yellow rectangle there. All right, so these 3 different methods are going to give us 3 different approximations, but it's just consistent. We're going to use more rectangles. So for every rectangle, we're going to use the same one, whether the left side of the rectangle, the right side, or the midpoint. All right, so now we'll go through some examples and figure out how we can do these approximations by hand. All right, so the first thing is we're looking at the graph x squared. And if we look at that graph, it's going to look something like this. All right, and we have it from 1 to 4. Right. And we're going to approximate this area. So if I kind of draw this line straight up, this blue area here is what we're trying to approximate. So the first thing we're going to have to do is figure out how wide are our rectangles. So if we're going from 0 to 4, we're trying to cover a distance of 4, and we're breaking it up into 4 even intervals. So each rectangle has a width of 1. And then the next thing is now I know my widths, and now I'm doing a left-hand approximation. So for each little interval, I start at 0, I go right to the 1, so I have 0 to 1 is my first interval. I use the left-hand side to figure out that height. My next interval is from 1 to 2. I use the left-hand side of that interval to figure out the height. 2 to 3, left-hand side, and 3 to 4. So this is going to be my left-hand approximation for x squared. And now I just need to figure out each of these, the area of each of these rectangles, and then add them all together. So the first rectangle, remember rectangle has base times height. The base is 1 because that's the width of each rectangle. And the height is the left-hand side, which is when I put 0 into my expression. And that's just going to be 0. All right, so this first rectangle has no area because it has no height. The second rectangle, the width is always 1. Now I put the left-hand side of my second rectangle in, which is 1. And that's going to give me 1. My third rectangle, width 1. All right, they're all going to have the same width. Now I plug 2 in because that's the left-hand side of my third interval. And that's going to give me 4. And the last one, the width is 1. And my fourth rectangle, 3 is on the left. So I'm going to plug 3 into my equation and get 9. And my final answer for my area is I just add all these rectangles together, and I get 14. All right, so my first estimate for the area under x squared from 0 to 4 is 14. If I wanted to get closer, I would do 8 rectangles or 16 rectangles, just more rectangles, and this number would get a little bit closer to the actual answer. In our next our next example, we want to do a right-hand approximation. So we're looking at the exact same function in the exact same interval, so we kind of know how to set it up. And again, we're going a distance of 4, breaking into 4 intervals, so our rectangles have length 1, but now we're doing a right-hand sum. So right-hand sum, our first interval from 0 to 1, we use the right hand and make a rectangle like that. Then 2 is the right hand of that next interval, 3, and 4. And so now these are the rectangles that we're dealing with this right-hand approximation. So our first rectangle, the width of it is 1, and the right-hand value is 1. And we plug that into our function, and we get 1. Our second rectangle, width 1, they all have the same width. So when we plug, so we're in this rectangle now, 2 is on the right, so 2 is what I plug in. I get 4. Third rectangle, we're here. 3 is on the right, so that's what I'm going to plug into my expression and get 9. And our fourth rectangle, 4 is on the right, and we get 16. And then for our final area, again, we have all these rectangles. We add them all together, and we're going to get 30. All right, so we did 2 different approximations. Our left-hand approximation gave us 14. Our right-hand approximation gave us 30. Our right answer is going to be somewhere in the middle, because our previous example was under. This one has a bunch of extra pieces we don't actually want. So our final answer is going to be somewhere in the middle between those two numbers. I'm going to do one more example, just using a midpoint approximation. So now we're looking at a different expression. But we're going to do a midpoint approximation. All right, so if we look at the graph, it's not completely important for you to know what the graph looks like, because the math is still going to be the same all the time. But we have a graph that looks like this. And the first thing is to check how big are our intervals. All right, so from 1 to 3 is a distance of 2. And we break it into 4 intervals, means our gap is a half. I'm just going to use decimals because we can use the calculator to kind of help us. All right, so each of our intervals is a width of 1/2. All right, so my first interval is going to go from 1 to 1.5, and then 1.5 to 2, 2 to 2.5, and then finishing at 3. All right, so that's going to give me my intervals for each rectangle. And then we're doing a midpoint approximation. So for each of these intervals, I'm going to take the point in the middle, and that's going to give me the height of my rectangle. And so I'm just going from the middle of each interval up to my graph, and that gives me the height. All right, so that is what my approximation is going to look like for my midpoint approximation. And now he's got to find all the areas. All right, so our first one has width 1/2. They're always going to have width of whatever that interval length is. And then what am I plugging into my function? I'm plugging in the midpoint between 1 and 1.5. So the midpoint formula is you add the two values together and divide by 2. You're basically just finding the average of the values. So if I took 1 plus 1.5, added them and divided by 2, I would get 1.25. So that is the number I'm going to plug into my function. And that's the area of the rectangle. I'll do them all in the calculator at the same time at the end. Our second one has a width of 0.5. And the thing I'm plugging in is the midpoint between 1.5 and 2. That's 1.75. The next one is on our third rectangle between 2 and 2.5 is 2.25. Plugging that in to get the height of my rectangle. And the last one, again, same width. And it's between 2.5 and 3, so 2.75 is what I'm going to plug in. So my last few steps is I'm just going to plug all these into a calculator to figure out the answer for the area of each rectangle, and then I'm going to add them all together. So after doing that, we get these values on the right, or just the areas of each rectangle, adding them all together and get 10. All right, so this is a midpoint approximation. One thing that's actually interesting about this problem is this actually ends up being the exact area because we have some extra bits that are in our rectangles, but at the same time we're missing some pieces of our answer and they kind of cancel out and we actually get the exact right answer for this approximation. All right, so here's one for you to try on your own. All right, you're using 2 intervals and a right-hand approximation to approximate the area under 5x plus 2. All right, so go ahead and pause the video and try that one on your own and see if you can do this approximation. And your final answer should look something like this. So the first thing is, how wide are our intervals? We're doing a distance of 4 from 1 to 5, breaking it up into 2 intervals. So those intervals have a width of 2. So we start at 1, go right 2 to 3, go right 2, and we end at 5. All right, then we're doing a right-hand approximation. So our first rectangle has a width of 2. That's the width of all of our rectangles. And the right side of that first interval is 3. So 3 is what I'm plugging into my function expression. Simplifying all that, you get 34. Our second rectangle, the right-hand side is 5, so I'm going to put 5 into my function expression. Simplify, you get 54. Add up your 2 rectangles together to get your final answer. All right, so those are the kind of 3 main ones. Actually, the left and right approximations are the most important. Midpoint is kind of just another one to do that's slightly more accurate than the left and right. And then there's actually a fourth one, which is known as the trapezoidal method. So in the trapezoidal method, all right, you're going to end up having the left side of your interval and the right side of your interval, and you're actually going to have different heights. And you create this trapezoid, which is like a rectangle with a slant, and the area of the trapezoid is the base. All right, so the base is there. And then you take the average of the height. So you have these 2 different heights on the left and right. Take the average of them, and that gives you the area of a trapezoid. So very similar to our other ways of approximating area, we're just kind of using both sides of our interval instead of one side.